Here is a combined summary of the 4 pages. This research investigates the efficiency of local treatments on Markov Decision Processes, MDPs, for improving inference and average treatment effects. It demonstrates the efficiency of classical inference methods, including model-based estimation and temporal difference learning under a fixed policy, as well as classical A/B testing with general treatments. The study introduces a variance reduction technique that exploits the local treatment structure by sharing information for states unaffected by the treatment policy, achieving a linear reduction in variance with the number of test arms for a major part of the variance. The research explores scenarios with perfect knowledge of the control arm, designing estimators that further improve inference efficiency. By leveraging the local structure of treatments, the approach optimizes data utilization from A/B testing within an MDP environment, concluding that this approach is optimal for improving inference efficiency. An illustrative example on improving customer lifetime value is provided, where the research utilizes the recency, frequency, monetary value, RFM, framework to model customer lifetime value using value functions. The objective is to estimate the average treatment effect, 8, of the coupon policy on customer lifetime value. Single-state treatment, SST, is employed, where the coupon is applied to customers with high recency. Efficient inference is achieved through model-based estimation and temporal difference, TD, learning, both methods being equivalent and asymptotically normal. A variance lower bound for unbiased estimators is derived, highlighting the challenges and efficiency of the methods. Variance reduction is further achieved by utilizing the SST structure and leveraging perfect information about the control arm. The study generalizes its framework to encompass more general local treatments, demonstrating consistently positive treatment effects across all states before and after the intervention. This research paper explores experimenting on Markov Decision Processes, MDPs, with local treatments, focusing on estimating the long-term cumulative rewards of treatment and control policies. The authors highlight the importance of information sharing between states, which can benefit all states and improve estimation efficiency. They review related works in structure-aware experiment design and experimenting on MDPs with general treatments, including the seminal work by Farias et al. 2022, on the average reward setting. The paper's contributions include developing new estimation methods for the long-term cumulative rewards of a single policy, A/B testing, and a new estimator based on information sharing for the local treatment. The authors introduce key notations and structures, including the MDP, treatment policy, control policy, and average treatment effect, as well as the seminorm induced by a matrix and the diags operator for functions on the state space. The paper focuses on the single-state treatment, SST, policy, where a new intervention is applied exclusively in a predetermined, crucial, state. The authors define the treatment policy Pi-T and the control policy Pi-C, and introduce the discounted state visitation measure RP-S, which quantifies the likelihood of visiting state S starting from state S, under policy Pi. This measure is crucial in assessing the impact of the treatment, as the frequency of visiting the crucial state significantly affects the treatment's effect. The central research question is to estimate the average treatment effect, 8, increment equals VTVC, by taking into account the SST structure. The authors provide numerical results verifying the idea of information sharing and discuss the setting with perfect information of control, generalizing the analysis to general local treatments. The paper's organization and notation setup provide a solid foundation for the subsequent sections, which delve into estimation methods and theoretical results. In the context of Markov Decision Processes, MDPs, this research explores the inference of value functions under a fixed policy, presenting 2 methodologies: model-based estimation and model-free estimation. Algorithm 1 outlines the model-based approach, which leverages the reformulation of the Bellman equation to estimate the value function. In contrast, Algorithm 2 details the model-free approach, directly estimating the value function without model parameter estimation. Proposition 1 demonstrates that both methods yield identical point estimations of the value function, highlighting their equivalent theoretical properties in finite space and finite action MDPs without function approximations. The study underscores the significance of understanding the theoretical properties of both methods, acknowledging the ongoing debate between model-based learning and TD learning in the reinforcement learning literature. Furthermore, the research investigates the asymptotic inference of value functions in MDPs, focusing on the asymptotic normality of estimators under a fixed and static policy. The concept of uniform ergodicity is introduced as a crucial condition for the central limit theorem for Markov chains. The main theorem establishes the asymptotic normality of the model-based estimator, assuming uniform ergodicity of the induced Markov chain, which naturally extends to the TDBASED estimator. The asymptotic variance is characterized by the variance of instant rewards and transitions to other states. A lower bound for the asymptotic variance of estimating the value function is derived, demonstrating the optimality of the covariance matrix. This work contributes to the understanding of the statistical properties of MDP estimators, particularly in the context of TD learning, and provides insights into the behavior of value function estimators under different policy scenarios. In the context of Markov Decision Processes, MDPs, this paper explores the application of A/B testing for estimating the average treatment effect, 8. The authors introduce the experimental policy Pi1/2, which alternates between the treatment policy Pi-T and the control policy Pi-C, and arrive an asymptotic variance bound for the TD method. They propose algorithm 3 for A/B testing on MDPs, which involves executing the experiment policy for T epochs, splitting the trajectory into two datasets, and using either algorithm 1 or algorithm 2 to derive unbiased estimations of VT and VC. The authors proved the asymptotic normality of A/B testing using theorem 3, demonstrating that the difference in the estimators converges to a normal distribution with a specific variance. The paper also presents a lower bound for experimentation with general treatment, showing that the asymptotic variance of A/B testing cannot be further reduced under general treatment. However, the authors demonstrate that the structure of strongly stable treatment, SST, can be leveraged to reduce variance through information sharing between test arms. This is achieved by utilizing the Markov property to share information between different test arms, resulting in an unbiased 8 estimator with a smaller variance than traditional estimators. The central limit theorem with information sharing is derived, showing that the 8 estimator converges to a normal distribution as the number of trajectories increases. A comparison of the asymptotic variance of general A/B testing and A/B testing with information sharing reveals that the latter has a smaller variance, particularly in the crucial state, due to the additional shared information. This reduction in variance is attributed to the structure of SST, which allows for more efficient use of data. The implications of these findings for experimentation on MDPs and potential future directions for research are discussed. The research discusses the application of information sharing, in multi-armed bandit problems, MDPs, under sequential treatment strategies, SST. It highlights the decomposition of asymptotic variance for both estimators, demonstrating the structure of variance reduction. Theorem 6 compares the asymptotic variance of with general A/B testing, showing achieves at least an equivalent level of performance. The analysis focuses on the crucial state S1, where information sharing is not feasible due to potential differences in the transition matrix and rewards. The observed reduction in variance primarily results from sharing information across all other states. The study also presents a necessary condition for equality in the inequality, which involves fixed rewards or linear dependence in the state visitation measure. The findings are particularly relevant in contexts like A/A testing, where the amount of data used to estimate transition probabilities and rewards can be doubled. The research concludes with a lower bound for experimentation with SST, affirming the asymptotic efficiency of the information sharing estimator. In the context of Markov Decision Processes, MDPs, the authors explore scenarios where an experimenter has access to extensive historical user data, enabling accurate determination of customer transition matrices when not offering a coupon. This assumption is prevalent in various domains such as marketing, offline reinforcement learning, and healthcare applications. The proposed estimator BVTPI is generated by applying the Bellman equation with the estimated transitions and mean rewards. The difference between BVTPI and VC yields an estimator B increment pi of the treatment effects. Theorem 9 presents the central limit theorem of the estimator, stating that as t right pointing arrow infinity, the estimator b increment pi is asymptotically normal with a variance sigma pi. For the crucial state S1, the asymptotic variance sigma 2 pi, S1, exhibits a similar structure to the model-based estimator under a fixed policy, but with a significant reduction in variance. This reduction is attributed to the complete information on transitions and rewards for non-crucial states. The authors introduce notations sigma het pi and sigma home pi to facilitate a detailed comparison with A/B testing, both with and without information sharing. Theorem 10 characterizes the variance reduction of pi, stating that sigma het pi less than sigma het AB and sigma home pi equals 0 is less than or equal to sigma homus is less than or equal to sigma home AB. The parameter delta, measuring the difference between transition probabilities under the treatment and control, affects the variance reduction. The authors conclude that the proposed estimator b increment pi offers a more efficient way of estimating treatment effects, leveraging the perfect information on transitions and rewards for non-crucial states. The research also discusses the application of information sharing, as, and plug-in estimation, pi, for variance reduction in MDPs with multiple test arms. It starts by explaining how pi can outperform A/B testing even with information sharing, especially in heterogeneous components. The concept is then generalized to sampled transition, SST, with multiple test arms, where the control arm serves as a reference. The authors establish the asymptotic normality of the estimation for the SST, confirming the statistical robustness of their approach. The discussion then shifts to local treatment, where the treatment action is applied to a specific segment of the state space. This allows for a more flexible modeling of interventions in complex MDPs. The authors extend the results to local treatment scenarios, showing that all A/B testing methods, including IS and pi, will produce asymptotically normal estimators. The theorem characterizing this key difference from SST highlights the importance of state decomposition in variance calculation. The research concludes by emphasizing the significance of these findings in practical applications, particularly in scenarios where the number of test arms grows. The research applies multi-dimensional planning, MDPs, to optimize customer lifetime value through targeted treatments. It generalizes previous theorems to consider crucial subsets of states, demonstrating the diminishing effectiveness of importance sampling, as, with fewer shared information states. Synthetic simulations for two treatment types, SST and local treatment, show negligible bias across all estimators and a significant reduction in variance through IS and probability integration, pi. Pi outperforms IS in both examples, highlighting its capability in further variance reduction. The local treatment requires a substantially longer horizon for the standard error of IS to decay, illustrating the efficacy of IS increases with shared states. The discussion emphasizes the importance of fairness and welfare in MDPs, ensuring new treatments improve long-term outcomes for all states. The study also discusses the monotonicity of SST policies, ensuring positive treatment effects across all states, and addresses the bias-variance trade-off through the difference in Q, DQ, estimator and its variant, DQIS. Empirical results show both DQ and DQIS exhibit negligible bias and variance close to A/B testing and IS, respectively. The research paper systematically explores the application of treatment structure to enhance experimentation efficiency in Markov Decision Processes, MDPs. It begins by demonstrating the efficiency of an A/B testing algorithm for general policies and showcases how information sharing among tests can reduce variance for local treatment policies, surpassing the established lower bound. The paper highlights the trade-off between robustness and efficiency, emphasizing that efficiency gains from information sharing rely heavily on the local structure of the new treatment. It also discusses potential bias introduction by information sharing and the robustness of inference methods that do not utilize the local structure. The authors reference various works on reinforcement learning, experimentation, and statistics. The paper then delves into various aspects of experimenting on MDPs, including the importance of experimentation in evaluating policy effectiveness, methodologies such as multi-armed bandit experimental design, and the application of reinforcement learning in healthcare. It also addresses issues like interference induced by feedback loops in two-sided platforms and statistical inference after adaptive sampling for longitudinal data. The paper concludes by emphasizing the importance of considering equilibrium in experimentation and the role of reinforcement learning in improving decision-making processes. The supplementary notation section of the research paper introduces the vectorization operator vec, A, which concatenates the columns of a matrix A, and the matrix norm parallel X parallel A, defined as the square root of X transpose times A times X. The proof section focuses on policy sampling algorithms, specifically the major proof frameworks for asymptotic analysis in Markov chains. This includes the delta method and linearization, tracing back to Konda, 2002, and revitalized by Farias et al., 2022. The proof consists of 3 steps: Markov chain CLT, delta method, and linearization. The linearization technique, adapted from Lemma 6 in Farias et al., 2022, is presented in Lemma EC.1, showing that the variance of the linearized term G, Xi, equals the covariance matrix gamma. This lemma is crucial in establishing the asymptotic normality of the TD algorithm. The proof of Theorem 1, which establishes the asymptotic normality of the TD algorithm, is then presented. The model-based algorithm in Algorithm 1 is analyzed directly, and the convergence of Kt and Rt to K micropi and R micropi, respectively, is demonstrated using the Markov chain CLT. Finally, the delta method is applied to estimate Cp pi and Cr pi, and the asymptotic normality of the estimator BVMB is derived. The covariance matrix sigma is also obtained using the linearization technique. In the subsequent sections, the authors derive the linearized part of the function g, denoted as g, Xi, consisting of 2 components: linear reward and linear transition. By rearranging the terms, g, Xi, is rewritten as the sum of 2 components, g1 and g2. The authors then compute the covariance matrix sigma g, which is equal to the variance of g, x1, since the covariance between g, x1, and g, xk, is 0 for k is greater than or equal to 2. The variance of g, x1, is further decomposed into the sum of the variances of g1 and g2. The variance of g2 is computed as the inverse of I gamma p pi, multiplied by the diagonal matrix of sigma 2 pi, s, micro pi, s, and the variance of the value function v pi. The final covariance matrix sigma mb is given by the inverse of I gamma p pi, multiplied by the diagonal matrix of sigma 2 pi, s, micro pi, s, plus the norm of gamma v pi squared times sigma ps, micro pi, s. In the proof of Theorem 2, the authors establish the asymptotic efficiency of the TD algorithm by deriving the constrained Kramer-Rao bound, CCRB, for the MDP system controlled by parameters theta equals p pi, r pi. The CCRB is expressed as the inverse of the covariance matrix sigma mb. The authors also provide the partial derivatives of the value function v pi with respect to the transition probability matrix p pi and the reward function r, which are used to compute the CCRB. Ultimately, the CCRB for v pi is shown to be equal to the inverse of the covariance matrix sigma mb. The authors present a comprehensive analysis of constrained Kramer-Rao bounds and asymptotic normality for A/B testing in Markov decision processes, MDPs. They derive the constrained Kramer-Rao bound, CCRB, for estimating transition probabilities and mean rewards, showing it as a diagonal matrix with entries consisting of the variance of transition probabilities and mean rewards. This bound is used to establish the asymptotic normality of A/B testing statistics, which converge almost surely to their expected values. The authors also demonstrate the asymptotic efficiency of A/B testing and information sharing in MDPs, providing a theoretical foundation for experimentation and policy evaluation. The results are based on the analysis of various matrices and vectors, including Ka and Ra, which are used to compute the asymptotic variance. The study's findings have significant implications for the design of experiments and information sharing mechanisms in MDPs. The paper explores the variance comparison of on-policy and off-policy sampling algorithms in Markov Decision Processes, MDPs, focusing on the linearized part G, Xi, as a function of transition probabilities and rewards for target and control policies. It discusses necessary conditions for equality of covariance matrices sigma G and sigma het, concluding that linear dependence of state visitation frequencies under both policies is required. In addressing the asymptotic efficiency of information sharing in MDPs, the paper treats observations as I.D. and derives the Kramer-Rao lower bound, CRLB, for parameters theta. This CRLB depends on variances of rewards and state visitation frequencies under both policies, as well as variances for states other than S1. The paper also analyzes the partial derivatives of value functions with respect to transition probabilities, providing insights into how changes in these probabilities affect value functions. This analysis is crucial for understanding MDP behavior under different policy settings and its implications for variance comparison and information sharing efficiency. The authors extend their results to multiple test arms, presenting theorem EC.1, which establishes the asymptotic efficiency of information sharing with n test arms. They define a vector-valued function y, Xi, and show that its sample mean converges to a multivariate normal distribution, deriving the covariance matrix sigma y. Applying the delta method, they calculate the asymptotic variance of the perfect information, pi, estimator, and further extend this to the case of multiple test arms. Finally, they prove theorem 10, establishing the asymptotic relative efficiency of the pi estimator, by comparing the covariance matrix of the pi estimator to the heuristic estimator. The research paper discusses the extension of A/B testing, importance sampling, and population interpolation to Markov decision processes with local treatment and multiple test arms. It provides a detailed analysis of the asymptotic normality of the average treatment effect estimates, including expressions for the variance components and overall variance. The authors also delve into the analysis of variance reduction properties of inverse sensitivity sampling and pure importance sampling estimators in multi-arm bandit problems. The paper proves the monotonicity of the self-importance sampling estimator, which is essential for understanding the behavior of the estimator in different scenarios. The findings contribute to a deeper understanding of experimentation on MDPs and the performance of these estimators in various domains such as healthcare, finance, and operations management. The authors provide additional technical tools and lemmas to support their research, including the performance difference lemma, which applies reinforcement learning theory to their single-point treatment scenario. They also present the Markov chain central limit theorem in two lemmas, establishing the convergence of the treatment effect estimators. Perturbation bounds are discussed, including the stationary distribution perturbation lemma. Constrained Kramer-Rao bounds are also presented, providing a lower bound on the variance of unbiased estimators. The authors describe their experiment details, including the simulation setup for the customer lifetime value example. In the context of Markov decision processes, they delve into the DQ theory for the discounted reward setting, discussing the naive and DQ estimators. The DQ estimator trades a small bias for substantially lower variance compared to unbiased estimators. The authors also apply the idea of information sharing to the learning of Q functions, resulting in the DQIS estimator, which exhibits significantly reduced variance compared to the original DQ method. Simulation results verify the DQ theory of bias and demonstrate the effectiveness of DQIS in reducing variance.